Good. How do we actually run the regression with interaction terms using R, right? So it is showing that. We're going to create a regression result matrix called reg underbar interact. And that will be the regression GLM, right? Generalized least squares model based on data OJ, whose dependent variable is log of sales, and explanatory variables are those variables related to this interaction term between log of price and brand dummies, right? Brand dummies. Now, this is a distinction, okay? You see very convenient command or the specification of the model over here, model. In SAS or Stata or other usual statistical languages, right? When you interact A and B variable, you have to write down A times B, right? But here in R, you just have to write down A times B, and it automatically throws in those A and B for you. This is fantastic because when you want to interact A and B with this, which is B is not just a one variable, but is a group of variables. For example, over here, the brand dummy variables, what do we have? Tropicana and Minute Maid, two variables in one set, brand, right? Interact with log of price. You just need one times, you just have to write it down instead of writing many times. And then imagine if you have 60 different brand dummy variables, right? In SAS, you have to write down like 60 different times, multiply, and then all those crazy things have to happen. But over here, you just have to write it once like this. Good, so let's go. Here the coefficient of the regression is shown, intercept and log of price, its coefficient. Is it sensitivity or elasticity? Elasticity, just a reminder. And then you have coefficient on the dummy variable of Minute Maid brand dummy over here, and then Tropicana brand dummy, that coefficient. And what is important is the interaction terms coefficient, right? Minute Maid interacted with price, this one. And then Tropicana interacted with log of price, the elasticity. So how do we interpret this result? Well, let's start from the default, which is Dominique, right? Dominique, our base case or reference, that Dominique's price elasticity is minus 3.3775. Okay, that's this guy. Excuse me, right? Just to make sure you're wake up. How about Minute Maid? Well, that's elasticity of default and the interaction term, this guy, right? Adding these two together, it makes it like minus 3.32, right? How about Tropicana? That's this guy plus that guy, right? That's minus 2.71. Okay, so we have three different price elasticity of demand. Which brand has the most inelastic price, least elasticity with respect to price? Whose brand is not the demand is not changing that much? Okay. The same question is, regardless of how much price you change for this brand, the consumers doesn't move. They just keep on buying it, regardless of whether you increase the price or not. decrease the price. They keep on buying it. Which one? Tropicana, right? Podo, tok. Tropicana. It sticks into your brain. You keep on buying it. That's, the brand value, right? The brand strength. The elasticity is the smallest. Dominique's, they are moving faster, right? That's something you can see it. Okay. Advertisement, right? Advertisement. Well, a key question is what changes when we feature a brand. Here, this means in-store display promotion or flyer ad, that kind of, featuring, right? You could model the additive effect on log's sales volume. Expected value of log of sales volume should be equal to some intercept alpha plus a dummy variable of having features or not, right? Advertisement campaign versus not, dummy variable, okay? And then alpha over here will be feature specific coefficient, right? The dummy variable, its coefficient will be alpha. And then beta coefficient for brand and then log of price, you know that, right? Or this and its effect on an elasticity, right, like that, okay? So alpha b, right? And then beta log of p plus 1 times features and gather together like terms over here. You have coefficient on features plus beta times log of p, right? Or its brand specific effect on elasticity, or expected value of log of v equals the same alpha, same thing, all the way down to what? 3-way interaction terms, right? So here, what is that? The feature specific, brand specific, great brand specific elasticity, right? CDR code for runs of all 3 models and connect the regression formula and output of these equation yourself. We're going to cover this one next week, okay? And then logistic regression, linear regression will be, logistic regression is the next one that we're going to cover here, right? Those 3-way interaction terms is something you're going to do exercise yourself. We're going to cover that next week, right? And then logistic regression, well, you must have experienced this before in your big data course or whatever, but let's go through it. Okay, linear regression is just one type of linear model. It is not even the most heavily practiced technique. Logistic regression, when y is true or false, 0 or 1, black or white, dummy variables, right? Binary response, we call it, right? Bi means 2, okay? Response as a prediction target, your dependent variable. After all, after doing this data science, you want to predict something. Is this company going to go bankrupt or not? Is this company going to go for IPO versus not? Is this company, for example, LG Chemical nowadays, is this going to spin off its division or not? LG Chemical, they are thinking about what? The battery division that you guys visited last year for iCore project, right? Spinning off versus not. It's like a 0-1, okay, kind of changes, right? You want to predict that, right? So that's something you could try. Logistic regressions. Profit or loss greater than or less than, or pay or default or something like that. So personal bankruptcy kind of things. Is he or she going to default on his loan versus not? Thumbs up or thumbs down, buy or sell. Oh, stock recommendation, strong buy or not even strong, not strong buy at all. Of course, strong buy, and weak buy kind of things is not covered over here. Whether it is a strong buy versus non-strong buy, or buy or non-buy kind of things, right? Yeah, potential customers or not. We win or lose, or sick or healthy, Republican or Democratic, or like a chapa upa. Of course, there are some guys like me in the middle, right? Left wing or right wing kind of things, right? High dimension, in high dimensions, or Trump versus no Trump, right? In this election coming up. High dimension, it is often convenient to think binary. I mean, when it's more complicated, you want to reduce it because of your bounded rationality, right? It's like, let's keep it this way or that way, you know. The marginal error is not that important, so this or that kind of choices. Yeah, that's something you could think about, right? Building a linear model for binary response data, okay? Recall our original model specification is expected value of y given x should be a function of x times beta. The response y is 1 or 0, 0 or 1, leading to conditional mean, right? Expected value of y given x should be like this. Bernoulli distribution, Bernoulli distribution, kind of. Either you have jackpot or not. Probability of having it or the other probability of going bankrupt, kind of things. P times 1 minus P, kind of things will happen, right? And the result is 1 versus 0. So that when it is a probability of 0, I mean, not a probability 0, but the response is 0, right? When does that does not happen, right? The response function is, the result is 0. Well, whatever you multiply, right? It's 0, is 0, is 0, is 0. So nothing leaves there. But whatever is left is the case of having 1, bankrupt. And then its probability multiplied. That's what's going to remain as your response value. Okay? And the thing is, expectation turns out to be the probability itself. Make sense? So that's what's going on. We will choose the function of x times beta to give values between 0 and 1 like this. Okay? So let's go. All right. So probability, let's say this is a conditional probability of y1 given x values should be function of all this ugly linear combination of x1 all the way down to xp with a constant, and where f is a function that increases in value from 0 to 1 as your x times beta, okay, increases from negative infinity to plus infinity. Your probability, cumulative probability, starts from 0 to 1. Okay? That's what's happening over here. Your probability summation has to be 1, right? So you need some increasing function reflect your probability increase like that. So logistic function works like that. Normal distribution also works like that. So that's your choice. So we will use the logistic link and do logistic regression like this. Holy, what do you have over here? Well, this is something you have to live with, okay? Let's bite the bullet. Let's go together. What you have on your left-hand side is your probability of having y, dependent variable, equals 1 given x, right? We're going to model this with logistic function over here. The numerator is e to the power of x times beta, okay? The matrix multiplication going into your exponent of natural log e. What? Yes. And what you have in your denominator is 1 plus e to the power of this ugly guy. Why do we have this guy? Well, let's think about it this way. E to the power of x, well, that function actually, if you graph it, x and y, right? When x is Negative infinity is near 0, and it crosses 1, and it goes to like this, infinity, right, as increases. Yeah? And it crosses 1. Okay? Fine. That's numerator. Okay? Like, shall I say x beta? Okay? X beta or x, it does not matter that much. As this guy increases, it goes to the infinity, starting from slightly positive or near 0 to goes up like this. Well, that's numerator. Oh, that goes to infinity. Don't worry, because your denominator is even 1 plus this guy. So that it's going to be bigger than this guy anyway. The thing is, when this guy is negative infinity, this whole e to the power of x beta will be near 0. It will be near 0, and this guy will be near 0. As long as your numerator is near 0, the whole thing will be near 0. Okay? That's good. That's one part. How about when this guy goes to the infinity over here? Well, this guy goes to the wait. When this guy is 0, you hit 1, exactly 1. Okay? You hit 1. This guy will be 1. This guy will be 1. 1, 1, 1. Oh, what is that? 1 over 2. Half, right? At this point, the probability will be half. Oh, that's interesting. And you know this is strictly increasing. So starting from 0, it increases to 1. The probability goes to half. And then after that, what happens? Well, if it goes to infinity, it also goes to the infinity, so that it goes to 1. So if it goes to 1, the infinity, the probability will go to 1, like that. And then this is going to be half. So it will go like this. The logistic function, right, will look like that. S curve, right? Centered at half. That's this function. Holy, ugly term, you may say. Okay, that's just once in your lifetime. Okay, so let's go to the exponent part. X times beta is actually this wholly ugly term over here. You know that? Yeah. And then because this is the exponent, it's just straining your eyes. So to release that, your eyes, people usually represent it or show it as exp parenthesis and this exponent term over here. It's the same thing, representing in different ways, okay? Not to strain your eyes, okay? That's it. The logit link is common for a couple of good reasons. One big reason, a little algebra shows that this goes together with the probability ratio. We call it odds ratio, okay? Odds ratio. Probability of having it over not having it, okay? Probability of bankruptcy relative to probability of surviving. P over 1 minus P. That's odds ratio. Okay, take the log of it, right? Take the log of the odds ratio. That's this guy. Again, this log is base E, right? Natural log, right? Everything is natural. Okay, so what's that? Well, this odds ratio, we can let's model it, this odds ratio, with this what is it, the linear combination of those x variables, right? Constant x1 all the way down to xd, right? Your leverage ratio and your profitability kind of things, right? Your probability of bankrupt or not bankrupt, the odds ratio, is a function of linear function of log. Take the log of it, and it's a linear function of this guy. Well, fine. That's good. Okay, fine until now. Then what do we do? Well, because this is log, let's get out of this log. Well, 지수는 로그및 진수. You remember that, right? The exponent what you have on your left-hand side should be your exponent of natural log, the base of it, or e to the power of this guy should be what you're having it, over here. Ah, that's that. Good. So what do we do? What do we do? What do we do? Well, let's do the math, arithmetic. Take this guy to the other side of the equation. That's this one over here. P is equal to 1 minus P times that guy. And what do you have? Well, P is left over here. Well, take this guy to the other side of the equation. Yes, and gather together like terms, right? You have P on your left-hand side and then the minus P on the right-hand side. Take it out over here. That becomes 1 plus e to the power of blah, blah, blah times P. And the right-hand side, you have 1 times this ugly term over here. That's this guy. Now what? The probability should be this guy over here, right? Send this guy to the other side of the equation. And then that becomes this one. And that's this guy. Ooh, the probability comes from here. That's logistic probability. Okay, fine. Okay, so that is a linear model for log odds, right? Log odds. It works nicely with this odds ratio. Okay, interpretation matters over there. So wait for that one. Anyway, here the textbook author gives you spam filter data. Okay, work with this one next week, right? Your inbox does binary regression, spam versus non-spam. The response. Here the spam data is about email filtering, right? Spam filtering automatically, whether this email is a spam versus not, right? 1 versus 0. That binary response will be there, right? And then spam CSV. It has actually 4601 emails observations, right? 1800 of them about will be spam. The remaining is non-spam, categorized. And then the word and characteristic, right, of this email, each and every 4600 emails are characterized as a dummy variable or the how much it shows up right over there. How many times such word shows up, right? Character presence in indicator, 0, 1 dummy, okay, actually, right? The dummy variables. For example, right? George, that word, does that show up versus not? George, a guy's name, right? Andy may be there, right? Yeah, and then run some regression on it. Logistic regressions like this, and then this is GLM in our code. Again, y tilde x data, and then family. You just have to specify. The family should be binomial, right? Binomial means 0, 1 response. The argument, indicates this is binary. The response can take a few forms. Y equals 1 or 0 numeric vector, or y equals true, false, Boolean or logical variable, or it could be win or lose kind of text string, right? Only 2 kinds, by the way, not multiple. Bankrupt or not, healthy versus not, kind of things. Everything else is the same as for linear regressions. Yeah. And then perfect separation. Well, we're going to create a data set based on regression results, right? Regression results matrix called spammy. GLM model is used, logistic regression, spam, tilde, everything. So tilde dot, right? Tilde dot means like spam is your response variable and the other whole variables. You check out the data set, you're going to see a whole bunch of explanatory variables on the right hand side, which may be troublesome, but let's just forget it and run it. Okay, fine. There will be a warning message like this. Ignore it. We are warned that some emails are clearly spam or not spam. This is called a perfect separation. we don't need to worry. Okay, the situation can introduce numeric instability in your algorithm, mess with standard errors, mess the p-values, etc. Multi-collinearity issues will be there, but it is largely benign. Okay, fine over here. Okay. Just as a first baby step, let's just do it. It occurs where here because some words are clear discriminators. So for example, word underbar George. This is a dummy variable that is 1 if the email has the word spelled George. Okay? The thing is, whenever George comes up, it's a specific person's name, it's less likely to be spam. I mean, everybody has some experience like this. Okay, you got some emails from Nigeria or whatever countries, and then say what? Hey, sir. They don't say, hey, Andy, right? Hey, Younghan. No, they say, dear sir, or dear beloved guys. Here is a widow with left with millions and billions of dollars, and then we want to share with you. Here's a business opportunity. Click here. That's a spam, right? That's why. Less likely to be spam when it is George over there. Okay? That's the message. The next. The model over here is like this. Interpreting the coefficient, right? The model is like this. So you have odds ratio probability over 1 minus probability. It should be equal to exponent of beta, right? Like this. So exponent of beta is the odds multiplier for a unit increase in xj. Okay, odds multiplier. So beta of word George is minus 5.8. So George in an email multiplies odds of spam by exponent of e to the power of, okay, e to the power of minus 5.8, which is 0.003, okay? And then the beta coefficient of character that has character of dollars, right? The email that has dollar sign, right? That dummy variable, capturing whether it has dollar sign or not, that dummy variable's coefficient is 1.9. So what do we do? Okay, e to the power of 1.9 is 6.5. Okay, so that's the odds ratio increased by 6.5 times. Okay. On the other hand, the word George, right? The odds ratio turns out to be 0.003 as opposed to 1. 1 is probability of having spam versus not equal, right? Odds ratio 1. But odds ratio 0.003 is like, what's that? 300 times smaller chance of being a spam over there, right? That's George. 300 times smaller. Whereas character dollar, 6.5 times bigger chance of being a spam than not. Then that's this interpretation of this, right? Then what is the odds multiplier for a covariance coefficient of 0? E to the power of 0 means what? Whatever to the power of 0 should be 1. Odds ratio 1 means what? Probability of being, right? Spam versus not is the same. Okay, doesn't affect anything, right? That's it. Intuitive, right? Intuitive. The odds of being the spam versus not, it doesn't get affected by any variable whose coefficient is 0. Yeah. It does not affect anything. Intuitive result. Summary function gives the coefficients plus some other information. The bit at the bottom is especially useful. So go ahead and try this regressions and then get the summary results like this. These are the stats on fit, and they are important in either linear or logistic regressions. Understanding deviance ties it all together. Deviance is something we're going to talk about from now. You can think about it as like a distance, deviance, deviation, getting away from what is predicted, right? The difference, the residual kind of things, deviance. Remember, OLS was about minimum least square distance, right? Distance, least square distance. Here we label it in deviance term, right? Deviance term in logistic regression, because this is non-linear, right? Non-linear, like curved things, right? So deviance, estimation, and fit. Well, let's see. Two complementary concept is here. Deviance refers to the distance between data and fit, predicted value, and then actual realization. Actual realization is data. Fit is the predicted value. You want to make it as small as possible. Minimum deviance, least squared distance. The same idea. Likelihood is the probability of your data given parameters. What? Likelihood? I had a long time understanding this part. Okay, if it troubles you, you are not alone. Don't worry, you are not alone. I am here with you. Yes, likelihood. Okay, you can understand it as a probability in essence, right? But we take a different perspective. What do you mean? Here, I mean, in the probability or OLS regression kind of things, you're looking at it from the perspective of the data observation, all those realization, data point, and you are estimating the beta. Okay, that satisfies the least squares distance. In likelihood, you are taking the data as fixed, and then you are more interested in the coefficients, right? Coefficients. And then the coefficients that minimizes this probability. Okay, you are taking the derivative. Take the derivative with respect to, okay, with respect to beta. Take the derivative with respect to the slope terms instead of the x. Oh my God, that's strange. We've been taking derivative, right? Take the derivative of y, derivative of y, or differentiate y with respect to x. Hey, let me write it down over here. Y, okay, y is equal to a plus bx, and then take the y y prime was b, because it was like take the derivative of y with respect to dx over here. That was b, the slope, right? That was conventional perspective, looking at x only, right? But the funny thing over here in the likelihood is look at beta, right? And then forget about x for now and take derivative with respect to b, so that the overall probability, right? The overall probability based on this data will be minimum. The deviance, okay, the deviance based on this result will be minimum. Okay, take the derivative of y with respect to beta. There will be some first order condition that has to be 0 or something. Okay, and then that is the point. Here is the beta. Okay, and here is the y. Okay, instead of x, you have beta, and we are presumably the likelihood function will be curved like this. Okay, maximum likelihood, and this is the beta hat. The beta that maximizes the likelihood, maximizes the probability, that satisfies the data, that fits the data very well, so much so that it will minimize the deviance between the data and the predicted value, the fit, right? That's the idea of maximum likelihood function approach, maximum likelihood estimator, MLE, maximum likelihood estimate. We're taking a different perspective, right? A beta perspective instead of X perspective. That is terribly difficult to do it. Okay, that was taking a long time to do it. What the heck are we doing with this maximum likelihood? But this is it, right? So likelihood is the probability of your data given parameters. You want to take it as big as possible. Likelihood maximum, deviance minimum. Yeah, deviance should be defined as -2 times log of likelihood plus some constant. C is a constant that you can mostly ignore, partly because the sheer calculation will be crazily complicating your eyes, screwing up your eyes unnecessarily. So just take it as it is. Likelihood, that's important. Take a log of it. You will see why we take the log. -2 because it's just convention, and then it's like we want to minimize the deviance, right? Maximum in likelihood will minimize the deviance by multiplying it by minus, and 2, you will see the convention like that. We will think of deviance as a cost to be minimized, and anytime you do the machine learning kind of things, you want to minimize the cost of computing, right? And then this reference is referred to as maximum likelihood estimate, or MLE. Don't get spooked. Okay, fine. Maximum likelihood, least squares and deviance in linear regression. Well, it's I'm trying to discuss this MLE, maximum likelihood, based on normal probability function. Okay. Of course, we talked about the logistic function, right? We're going to get back to that logistic, but the normal distribution function is another one that we use, called the Probit model. Probit model using normal distribution, Gaussian function, we call it. The Gauss invented, the regression guy, the best mathematician, right? Mathematically, this is beautiful and complete, so that people often use it. Logistic regression is another one. Logistic or Probit, Logit versus Probit. They are representative two models working with this binary response, 0, 1, 0, 1, black and white model, bankruptcy versus not, either Logit or Probit. Okay. So probability model, let's say y follows some normal distribution with x times beta, comma, sigma squared, right? Sigma squared with some normal distribution. But after a certain threshold, it's going to take 1, and otherwise it's going to be 0. That's the resulting outcome, right? Y outcome will be either 1 or 0. But between this 0 and 1, when we predict, right, outcome is a resulting number, but when we predict y, it's not just going to be just 1 or 0. It's going to be something in between, some probability mass, right? Like in the end, the realization of bankruptcy is either you're bankrupt or not, right? So that's 0 or 1, right? 0 or 1, y, but right, y variable. But as you use this bankruptcy prediction model, you're going to end up with the probability of bankruptcy. Oh, here is a historical bankrupt happening or not, but based on this data, with this leverage ratio and profitability, well, the likelihood, the chance, the probability of hitting bankrupt will be somewhere between 0 and 1. The continuous value will be predicted That's what I'm talking about. And this predicted probability, let's say it is following some normal distribution. That's the idea over here. So normal distribution function, you remember this ugly formula, right? Yeah, how did you write all these things? You know how to do that in my YouTube webpage, right? So you can do it quite easily over here in PowerPoint, by the way, with your hands. Don't need to stick in and draw your pictures, anything. You will be very fast anyway. Given n independent observations, the likelihood will be like this. Likelihood, n observations. So each observation of your companies, right? There will be bankruptcy, the probabilities, right? Like this. Either bankrupt or not, so starting from 1 to n, there will be a probability, right? Starting from some near 0 to continuously going up to 1, like there will be some probabilities. Each and every observations, let's say. And then that will be what? Normal distribution like this for each observation. Normal distribution. And the thing is, the likelihood that we talk about is a probability for each company, but not just that. You have n different companies, you multiply this thing. We are assuming some kind of independence over there between these, among these companies, right? Multiply these probabilities from observation 1 all the way down to last observation. So that's multiplication. Product is represented using this big, ugly sign over here, which is called pi. Product P, pi, Greek P. That's why pi is over here. Holy cow, multiplying, cumulatively multiplying all those things from 1 to n. Holy cow, how do we do that? Well, that's this one. The first observation probability, right? The first company's probability of going bankrupt will be like this using normal distribution. And then second company, you just multiply it, and then all the way down to n different companies' probabilities, right? That's this. Holy cow. One term is ugly, and you are multiplying n different multiplication over there. You are right. This is ugly. But here comes an interesting thing. I say this whole ugly calculation will be proportional to the following, which is exponent, which is e to the power of, it's the same thing I said. The power, right, the exponent will be like this, the big square bracket. And then all those things minus half will be over here commonly. And then the thing is, it is exponent. So multiplication of e to the power of these exponents should be e to the power of summation of all these exponents. You see that? The multiplication becomes summation as long as it is in the exponent. That's what this math more tractable or more doable, right? Summation. It's nothing but summation. Good. Fine. And then what? Well, you don't need to worry about all other ugly terms. What you need to worry about is that this leads to a deviance. You look at this over here. What matters over here is this guy. Forget about this, that, or that, right? It's just the, there. But what matters is this, the variable part, right? And this is y minus x beta squared form. Yeah, this one, forget it. This one is just another constant, right? Forget it. So that's this guy. And remember, we want to minimize the deviance, which is equivalent to minimizing the residuals. And that, what was the residual? Well, that is nothing but y, the realized value, minus the predicted value, x times beta. That's epsilon. Oh my God, epsilon squared, by the way. And summation of epsilon squared. That's nothing but OLS, right? OLS. Minimizing deviance is the same as least squares, right? And thus the MLE minimizes our sum of squared errors. I see. That's what's going on. Our MLE for logistic regression works the same way, but with a different probability function. Instead of Gaussian function, we have logistic function over here. Likelihood, again, this is probabilities, products of probabilities of all different observations in your sample, random sample. And then that's probabilities of what? Having one outcome as opposed to the other outcome. Either have it or not, right? P or 1 minus P, and then you have y times 1 minus times y. What the heck does that mean? Well, when you have bankruptcy, that's this guy. When you don't have bankruptcy, that's this guy. Okay? Y will be dummy variable 0 or 1 in this logistic setting, right? When you have bankruptcy, this guy is 1, so that you have P. When you don't have bankruptcy, this guy, okay? You don't have that bankruptcy, so this is 0, and this guy becomes 1, and then that guy survives, whereas this guy disappears, right? So you will have either of the two cases, bankrupt or non-bankrupt, like this, all right? So that's what's going on. And then bankruptcy probability is what? This ugly term. And then non-bankruptcy probability is 1 minus this guy, which will be 1 only, because 1 plus that ugly term minus that ugly term again. That cancels out. 1 is left. Make sense? And then this guy, multiplication, by the way. And then product, multiply, 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 multiply. Each different cases of bankrupt or not, right, is multiplied all across n different observations. Holy cow. Yes, that's what's going on over here. Okay, fine. Then move it, Andy. All right, yes, move it. This is maximized by minimizing the deviance. And then we do it minus 2 times log likelihood function, as I said before. That's minus 2, and bring that ugly term over here, and you will realize if you do the math and arithmetic, and it's going to be proportional. Again, it's going to be proportional to the summation of these ugly term over here. How do you do that math? In the end, it's going to be like this, right? How do you do that math? The next page will discuss that mathematical arithmetic, so you can do it in your pleasure, free time. All we've done is to take the logarithm and multiply by minus 2, as you see over here, log, right? Yeah, and then the next page shows the holy arithmetic. Holy cow. But just once in your lifetime, at least twice, please, actually, write it with your hands and see and realize what the heck is going on. Oh my God. And then log function of all these things makes the product or multiplication into summation. And then, you know, the ratio becomes minus, and then something gets cancelled out, and then you see very simplification over there, and then what you have to worry about is all these only this part. You will realize it. Okay, I hope you like it. And then we have the same output as for a linear Gaussian model, but the dispersion parameter here is always set to 1. Check this to make sure you actually run logistic regressions, and then the result will be like summary spammy will show it. The degrees of freedom is actually the number of observations minus df, where df is the number of coefficients actually estimated in the model. So if you have p coefficients, that will be the df, right? So you will see what's going on there once you have it. Sum of the squares or deviance is the bit we need to minimize. Okay, deviance should be proportional to that guy, summation of y minus x beta, which is epsilon squared, right? And this makes the observed data as likely as possible. Error variance, sigma squared, measures the variability around the mean, and sigma squared over there, by the way, should be variance of epsilon, where epsilon I should be this, are the residuals. R estimates sigma squared and then calls it the dispersion parameter. For example, in our output for our linear OJ regressions, dispersion parameter for Gaussian family taken to be 0.48. Even if we know beta, we only predict log values, log sales with uncertainty. There is a 95 probability of log sales in x beta plus minus 2 times square root of 0.48. Okay, so that's basically it. And then residual deviance D is what we've minimized using x beta. Null deviance D0 is for the model where you don't use x. That is, if you use y hat, should be y bar, then D0 should be yi minus y bar squared and summation. In linear regression, D0 will be something like this. Okay. In logistic regression, the difference between D and D0 is due to information in X, and then the proportion of deviance explained by X is called R squared. R squared should be D0 minus D over D0, and then that will be 1 minus D over D0. This measures how much variability you are able to model. And then in spammy stat or the regression results, R squared will be 0.75. In OJ reg, R squared will be 0.54. Now, R squared in linear regression, these formulas should look pretty familiar. R squared should be 1 minus SSE over SST. Sum of squared errors, sum of squared total from statistical classes, and then linear deviance is just the sum of squares. And you will also recall that R squared should be correlation squared, right? Between y and the predicted y in linear regression, where y hat denotes fitted value. Excuse me. Yeah. And then, right, so for linear regressions, minimum deviance should be maximum of maximizing the correlation between y and y hat, and the y versus y hat makes a straight line. You have a perfect fit. Then fit plots for logistic regressions. We can plot y hat versus y in logistic regressions using box plot, right? Box plot. Well, spam mail versus non-spam mail, right? Fitted values, right? Fitted values of probability, right? It is shown in this box plot. Well, here you separate these data into actual spam mail versus actual important or non-spam mails, right? Right-hand side versus left-hand side. And then the predicted value of this mail being spam is shown over here in the red box, okay? The predicted value of being spam, okay? Or not, right? Being spam very high. And there are some spam mails whose predicted probability of being spam is very, very low indeed. But absolute majority of them have very high scores over here, right? High probability, predicted probabilities. In contrast, if you look at non-spam mails, right? You see the predicted probability of being spam is extremely low, massively low. And then, of course, among these important, the classified, and then the important mails, right? Important mails. There are some mails whose predicted probability of being spam is very high, right? Very high. Of course, there will be always like type 1 and type 2 errors, right? These are those guys, right? The estimation pushes each distribution away from the middle. Where would you choose for a classification cutoff, right? It depends on your, you know, um, data analysis experience, and then the discipline as you work out. Okay, and then prediction. We've seen that prediction is easy with GLM. There, you just command is like predict, and then spammy, and then with this regression result data, the new data should be created, and then these guys will be showing up. 1 through 4 observations will be shown, 1, 2, 3, 4 like this. So go ahead and try it with your code. And this outputs x times beta for each x rows of my data, right? In logistic regression, to get probabilities like this, right? Add the argument type response and predict like this, and then you will have those results like that. Yeah, new data must match the format of original data. Keep that in mind. Out of sample prediction is an important thing, right? In sample prediction, well, everybody can do that, but out of sample predictability, right, is very difficult. You care about how your model predicts out of sample, right? That was not covered by your data thrown into your regressions. So how much does it predict and match with the reality, match with the actual realization? Okay, that's the issue. One way to test this is to use a validation sample. So validation, well, fit your model to the remaining training data and see how well it predicts the left out data. So it's like a splitting the whole sample into two parts. One is training set, and then the other is testing set. Okay. Whereas previously in your regression, we were not distinguishing training versus testing data. We were just using it as a whole thing was just used as the regression data. Okay. Whereas here you split the sample so that you run a regression with the training set. Okay. Yeah. And then sample 1,000 random indices. And then you divide or you specify leave out data. Okay, leave out. And then starting with the email data, okay, sample, random sample, right, 1,000 of them. Okay, 1,000 of them. Take it out as a leave out and train the model without these observations. So spam train data will be created, and then using GLM, and then the spam tilde everything, which means like, again, run the logistic regression using the whole explanatory variables. But in terms of the observations, don't forget, you take out those leave out observations in this regression, okay? And then you run the regression using the rest of it. Okay, that's what this command is about. And then predicted probability of spam on the left out data will be thrown into pspam data set. Okay, predict spam train and new data email leave out will be created like this. And then fit plots on the 1,000 fit out observations, left out observations, and then what? Here you classify, you have spam data and then versus import non-spam data in your leave out observations, and then all of these, right, based on their x variables, you can compute the predicted probability of being a spam, right? Predicted probability of being spam based on the right hand side variable. Okay. So spam class versus non-spam class, right? You still see absolute majority of them having high scores of being spam, high probability of being spam. And then non-spam emails, you have very low scores of very low scores of being spam mails, right? So you have some out of sample predictability over here. The deviance dot R has a function to get deviance from Y and predicted value. For the left out data, we get D0 1332 and D to be 562, R squared to be 58%. Since the sample is random, you might get different results. Notice that out of sample R squared is lower than in sample R squared, right? Which was 0.75, okay? This will always happen, of course, most of the time out of sample R squared will be 0. So that's the reality. So that's pretty much it for this week, and I hope you liked it. And then in case you have any questions, please email me. And not only that, I'm going to host some kind of office hours. And I also try to respond to you real time as soon as you email me, because everybody has a difficult time adapting to new language, R, and then this is kind of challenging. So I'm going together with you. I'm coming to the office every day. There's not much interesting thing going on in my life. I'm working here for you. So ask me questions. I will try to address those things as soon as possible. And perhaps on Monday morning or sometimes I'm going to make some office hour open to you guys, right? So let's talk together and see there, right? Hope you enjoy it, and then see you. Bye-bye.